Tonight, I'd like you to imagine that the world is gently closing its eyes with you. The noise of the day has softened into the hum of distant things, traffic far away, a refrigerator's quiet heartbeat, the faint sigh of the wind in the trees. Above all of it, higher and farther than your senses can reach, stretches the vastest canvas ever conceived, the night sky. Not simply blackness, not a void, but a living field of light and time and distance. Let's find a comfortable spot together, at least in our minds. Picture a blanket spread out on the cool grass. The fabric is thick enough to soften the ground, but thin enough to let you feel the earth beneath you. The air has that perfect balance between crisp and warm, the kind of air that makes each breath feel deliberate, almost ceremonial. You look up. Stars scatter above you like a patient artist has been at work for eons, placing each one exactly where it belongs. Some are sharp and white, like the reflection of the moon in a still pond. Others are tinged with blue or gold, faint embers in a cosmic fireplace. Between them, shadows stretch across distances so large that our words collapse under their own smallness when we try to measure them. In this stillness, a question stirs, not a loud, insistent one, but a quiet curiosity that feels as old as the light itself. Does this sky have an edge? Is there a point, somewhere far beyond what my eyes can see, where the stars simply stop? Where the blackness becomes something else entirely? It's a question that sounds like it might belong to children lying on their backs in summer fields. But it's also a question that some of humanity's sharpest minds have dared to wrestle with. Philosophers asked it long before telescopes existed. Astronomers and physicists have been refining their answers for centuries, and even now, in an age when we can send robotic messengers to other planets and detect the tremble of space-time itself, the question remains open, not because it's unimportant, but because the universe may not want to give us a simple answer. Before we can even begin to follow that thread, we need to talk about what space actually is. It's tempting to think of it as an empty room, just a huge, silent container in which all the stars, planets, and galaxies float. For a long time, that was the prevailing image, space as a backdrop, unchanging and unmoving. But the truth is stranger, and, in its strangeness, far more beautiful. In the early 20th century, a man named Albert Einstein, his hair famously untamed, his mind even more so, proposed something revolutionary. Space, he said, is not a passive stage. It is a fabric, a thing that can stretch and warp, curve and twist, and it is inseparable from time. Together, they form what we now call space-time. Massive objects, stars, planets, even you and me, though on a scale too small to measure, bend this fabric. Imagine placing a bowling ball on a soft rubber sheet. The sheet dips under its weight. Smaller balls rolling nearby will curve toward it, not because the ball is pulling them directly, but because the surface they travel on is curved. This, in essence, is how gravity works in Einstein's view. So when we ask, does space have an edge? We're not asking about a flat, rigid floor with a wall at the end. We're asking about a dynamic, shifting ocean, one we are part of, one that might bend back on itself or stretch forever. We're asking about a fabric that holds everything from the faintest atom to the brightest galaxy, and that responds, however subtly, to all of it. I like to think of it this way. You are not in the universe. You are of it. Your atoms were forged in stars that lived and died long before Earth took shape. The calcium in your bones, the iron in your blood. These are the dust of ancient suns. And those suns themselves were arranged in patterns shaped by the invisible hand of space's own geometry. That means that in some quiet way, you and the night sky are not separate at all. You are two parts of the same story. Maybe tonight is about honoring that connection. We don't need to rush. The universe has been expanding for nearly 14 billion years. It will wait a little longer while we linger here. The goal isn't to sprint toward an answer or to pin down a precise measurement. Instead, it's to move slowly enough that we can notice the subtler details. The way starlight feels almost like memory, the way the darkness between stars is not empty, but full of possibility. And here's something comforting. You don't need to remember any of this when the night ends. You don't need to memorize terms or equations or keep track of how many light years we've metaphorically traveled. Space will remember for you. Its patterns, its physics, its quiet expansion. These will keep going, whether you're paying attention or drifting into dreams. For now, all you have to do is be here, in this shared stillness, the grass under the blanket, the stars overhead, the ancient light, older than all of human history, finally touching your eyes. It traveled across the bending, breathing fabric of space-time just to arrive in this moment, where you and it can meet. And somewhere, in that immeasurable vastness, is the question we're going to follow, not to answer it once and for all, but to walk alongside it, like a friend on a long night's stroll. Does space have an edge? Maybe we'll find that the edge, if it exists, is nothing like we expect. Or maybe we'll discover that there was never an edge at all, just an endless invitation to keep looking, keep wondering, and keep drifting among the stars. If part one was about lying back and letting the stars settle into your gaze, part two is about realizing that you're not just looking out into space, you're looking into a bubble, a strange, invisible bubble that surrounds you wherever you are, no matter whether you're in a quiet meadow, on a bustling city rooftop, or curled up by a rainy window. I know bubble sounds small, maybe fragile. We think of bubbles as things that pop in an instant, leaving nothing behind. But this bubble is enormous, so vast that if you tried to walk its radius at the speed of light, it would still take you over 46 billion years to reach its edge. And it's not made of soap or air. It's made of time itself. This is what scientists call the observable universe. It's the entire region of space from which light, or any signal at all, has had enough time to reach us since the beginning of the cosmos. And just as every person's breath makes a different ripple in the air, every point in the universe has its own bubble, centered perfectly on itself. That means you are in the center of your observable universe, and so am I in mine. There is no special location, only perspective. The concept is a little tricky, so let's paint a picture. Imagine waking up before sunrise in a valley filled with fog. You can see the fence at the edge of your yard, maybe the outline of a tree a little further away. But beyond that, the world dissolves into a soft white blur. You know there are hills, rivers, maybe even a town out there, but until the sun rises higher and burns away the fog, you can't see them. The fog, in our cosmic version, is the limit set by the speed of light. Even though light is incredibly fast, about 300 kilometers every second, it's not infinite. And because the universe has a finite age, around 13.8 billion years, light can only have traveled so far since the beginning. That farthest distance marks the edge of our observable universe. But there's a twist. The edge isn't frozen in place. As time passes, more light from more distant regions has time to reach us. This means our observable universe is expanding, not because we're physically moving through space toward those regions, but because light from them is just now catching up with us. If you could somehow fast forward billions of years, you'd find that your bubble had grown, revealing more of the cosmic landscape. Still, there's another twist layered on top. Space itself is expanding, stretching like warm dough rising in a bowl. This means some galaxies are moving away from us faster than the speed of light, not by breaking physics, but because the space between us and them is growing so rapidly. For those galaxies, their light, emitted today, will never reach us, no matter how long we wait. So even though our bubble grows, some things will always remain outside its reach. I sometimes think about the edge of that bubble like the shoreline of an infinite ocean. You can stand at the water's edge, watch the waves, maybe dip your toes, but you can't see the far side. The sea keeps going, beyond your vision, beyond your knowing. That's where the mystery begins, not at a wall or a fence, but at the place where sight itself surrenders. And here's something humbling. What we see inside our bubble is not the universe as it is right now. It's the universe as it was when the light began its journey toward us. Some of the galaxies at the bubble's edge may have changed beyond recognition, or may not even exist anymore. Their light is like an old photograph that finally arrived in the mail, decades after it was taken. It's precious, but it's also out of date. That makes our view of the universe a kind of time machine. When you look at the moon, you're seeing it as it was about 1.3 seconds ago. The sun? About 8 minutes ago. The Andromeda Galaxy? More than 2 million years ago. And those dim, distant galaxies on the edge of our bubble? Over 13 billion years in the past. Every night sky is a layered history book, with the pages arranged not by topic, but by distance. I find that strangely comforting. It means that when we gaze into the dark, we're in conversation with the past, not just our past, but the universe's. We're hearing from stars that have burned out, galaxies that have merged, light that has threaded its way through space for almost the entire history of time. It's a reminder that we, too, are temporary, but not insignificant. Our lives are brief sparks in a vast timeline, yet the light of what we do might travel farther and last longer than we can imagine. So as you picture this bubble, don't think of it as a barrier. Think of it as a gift. It's the set of all the stories the cosmos has had time to tell you so far. And tomorrow night, or 10 years from now, or 1 billion years from now, if there's still someone here to listen, there will be more. The question of whether space ends doesn't find its answer here, not yet. The bubble's edge is not the universe's edge. Beyond it may be more galaxies, more matter, more space, or something stranger still. But the bubble is where we begin. Our first map of the great unknown, drawn not with ink on paper, but with light on the fabric of the mind. So, take another breath. Let your shoulders fall. Remember the quiet meadow from part 1, or the city rooftop, or whatever place you carry in your mind as your private stargazing spot. The bubble is there with you, stretching out in all directions, humming with the faint light of billions of years. We are going to follow its curve, step by step, and see where it leads. And perhaps, in doing so, we'll find that the search for the edge is really the search for our own place in the story. If you've ever stood on a beach and stared at the horizon, you know the feeling of wanting to reach it. There's a line, sharp and perfect, where the sky melts into the water. It feels so close, as if you could swim toward it and touch it, but the moment you start moving, it slips away. The line is always ahead of you, always out of reach. That's just geometry on Earth. But in the universe, there's a version of this horizon that behaves in an even more elusive way. This cosmic horizon isn't painted in blue water and pale clouds. It's invisible, defined not by color, but by the limits of speed and the expansion of the very fabric of space itself. To understand it, we have to accept something strange. The universe isn't just sitting there like a static map. It's stretching, everywhere, in every direction. And it's not stretching at a steady pace. It's accelerating, as if some unseen hand were slowly turning up the dial. Scientists call the mysterious driver of this acceleration dark energy. We don't know what it is. We've never seen it directly. But we see what it does. Galaxies far away are receding from us faster than galaxies close by, and the farther away we look, the faster they're fleeing. This isn't because they have rocket engines pushing them away, it's because the space between us and them is expanding. Imagine you and a friend are standing on a giant, stretchy rubber sheet with tiny dots drawn between you. If the sheet is pulled from all sides, every dot moves away from every other dot, not because the dots are sliding over the surface, but because the surface itself is expanding. If the stretching speeds up enough, some dots will recede faster than you can ever run toward them. Now replace dots with galaxies and rubber sheet with space. This is our reality. There are galaxies so distant that their light, emitted today, will never reach us. Not in a billion years, not in a trillion, not in any conceivable future. The space between us grows too quickly for the light to bridge the gap. This point of no return is called the cosmic event horizon. Right now, calculations suggest that this horizon lies about 16 billion light-years away. That number is already difficult to picture. What does billion even mean when applied to light-years? But here's the emotional weight of it. Everything beyond that line is permanently cut off from us, not just in practice, but in principle. No matter how powerful our telescopes become, no matter how much time passes, no matter how advanced any civilization might grow, those places will never send us new light again. They are lost, not because they're moving too fast in the way we normally think about speed, but because the cosmic road itself is stretching faster than their signals can travel. The image that comes to my mind is a river in flood. You're standing on the bank, watching someone drift downstream on a raft. At first, you could imagine swimming out to them or throwing a rope, but then the current quickens. The water between you and them stretches wider. Soon, even the strongest swimmer couldn't reach them. And then, at some invisible moment, the speed of the current outpaces anything you could ever do. They're still there, but already they're beyond help, beyond even your shouts. In the cosmos, it's light that tries to cross that river. But beyond the event horizon, the current of expanding space sweeps it away. Even photons, the fastest travelers we know, can't fight the flow. When I think about this, I feel two emotions that seem contradictory, but somehow live together. The first is a quiet ache, a sadness for the wonders we will never see. There are galaxies beyond that horizon that may be blazing with newborn stars, worlds circling those stars that might host oceans, mountains, maybe even living skies. And yet, those stories will never arrive here. They will play out in a separate chapter of the universe, one we'll never get to read. The second feeling is gratitude, because the universe is also filled with galaxies that are still within our reach. We are alive at a time when the night sky is rich with light from billions of places. The window is wide open right now, and we can look out across distances so vast that even imagination strains to keep up. And perhaps the knowledge that some of it will slip beyond view makes what we can see even more precious. Here's something even stranger. The event horizon is not the same as the edge of the observable universe we spoke about in Part 2. The observable universe is about the past. It's the record of light that's already arrived. The event horizon is about the future, the limit of light that will ever arrive. We can see some galaxies now that are actually beyond our event horizon. Their ancient light set out toward us billions of years ago, back when they were inside the reachable zone. But because space is expanding so quickly, any light they emit today is already lost to us. Watching them is like looking at a friend walking away in the fog, knowing they've already crossed a border they can't return from. There's a gentle kind of humility in this knowledge. It reminds us that the universe isn't arranged for our convenience. The great cosmic drama will continue whether we watch or not. And maybe that's how it should be. Not every story is meant for our eyes. Some are meant to exist simply because they can, in corners of space we'll never touch. So, here we are, standing on the edge of a horizon that runs away. It's not a line we can chase. It's not a challenge to overcome. It's just a truth, a quiet, unyielding truth about the nature of an expanding universe. And perhaps the most human thing we can do in the face of it is to sit here, in our own moment, and listen to the light that still manages to arrive, carrying with it the echoes of a place that might already be gone. As you close your eyes tonight, remember this: you are living inside a moving window, one that shows you a slice of eternity in both directions. What you see tonight is unique to you, to this instant in cosmic history. And somewhere beyond the horizon, the universe is still unfolding, endlessly, whether or not we ever get to see it. When you think of fossils, you might picture the hard imprint of a fern in stone, or the spiraled shell of a creature that swam in an ocean millions of years ago. Fossils are pieces of the past made solid, tiny fragments of history preserved against the rush of time. In astronomy, we have fossils too, but ours aren't locked in rock or buried in the earth. They travel, endlessly, through the cold emptiness of space. They are beams of light, photons, that set out on their journey billions of years ago, carrying with them a memory of where they came from. By the time they reach us, they've been stretched, bent, and scattered by the expanding fabric of the universe. But they still arrive, whispering stories of a time so ancient it's hard to imagine. When you look up into the night sky, you're not seeing now, you're seeing then. Even the stars that feel close, bright enough to make you squint, are actually little postcards from the past. The nearest star beyond the Sun, Proxima Centauri, is more than 4 light-years away. That means when you see its light tonight, it left that star over 4 years ago. For the Andromeda Galaxy, your eyes are catching light that began its trip over 2 million years ago. And for the faintest smudges at the edge of the observable universe, you're looking more than 13 billion years into the past, nearly to the dawn of time itself. That's the thing about light. It moves quickly, faster than anything else we know, but not instantly. And in a universe as vast as ours, even the fastest traveler needs ages to get anywhere. Every time you look deeper into space, you're also looking deeper into time. The night sky is a time machine, and you've been using it your whole life without even realizing it. This is where the metaphor of fossils becomes so fitting. Just as a shell pressed into stone preserves the shape of a creature long gone, light preserves the image of a galaxy as it once was. But unlike a fossil on Earth, which sits in one place waiting to be found, these cosmic fossils are always moving toward us, and they may come from places that no longer exist in the form we see them. Imagine a galaxy whose light left when the universe was a quarter of its current age. In the time since, that galaxy might have merged with another, been stripped of its gas, stopped forming new stars, or even been torn apart entirely by gravitational forces. And yet, here we are, looking at it as if it were still young, as if those changes had never happened. It's like having a conversation with someone who has already changed beyond recognition. You're speaking to their past self, and they will never hear your reply. I think there's something deeply moving in that. It's not just the science, it's the poetry of it. The light from a distant star is not only a measurement, it's a messenger. It left before humanity existed. It traveled without stopping, without resting, for billions of years, through voids so empty they make even the loneliest places on Earth feel crowded. It may have passed near other galaxies, been deflected by the gravity of massive clusters, and stretched by the expansion of space. And after all that, it arrived here, tonight, to land gently on the back of your eye. In astronomy, there's a particularly important fossil of light, the cosmic microwave background, CMB. This is the oldest light we can see, the afterglow of the Big Bang itself, released when the universe was only about 380 years old. Back then, the universe was hot, dense, and filled with a glowing fog of particles. Light couldn't travel freely, it bounced endlessly between electrons and protons. But as the universe expanded and cooled, those particles combined into neutral atoms, and light could finally move without constant collisions. That light has been traveling ever since, stretched into microwaves by billions of years of expansion. We've mapped the CMB in exquisite detail. To the naked eye, it would look almost uniform, the same in every direction. But sensitive instruments reveal tiny variations, slight warm and cool spots, patterns that are the fingerprints of the universe's earliest structure. They tell us how matter was distributed in those first moments, and from that, we can trace the growth of everything: galaxies, clusters, stars, planets, and eventually, us. But here's the catch. The CMB, as ancient as it is not the beginning. There was light before it, but the universe was so dense and opaque that no photon could travel far without being absorbed or scattered. That earlier time is forever hidden from direct view. We can only infer it from theory, like trying to guess what a room looked like before the curtains were pulled back. When I think about these fossils of light, I'm reminded of an old wooden chest filled with letters. Each one comes from a different time, written by a different hand, and yet, they're all addressed to the same place. You, here, now. You can't respond to the writers. You can't change their words, but you can read them, learn from them, feel connected to the moments they describe. That's what the sky offers every night. A chance to open the chest and read the letters, even if the senders have long since vanished. And maybe, in some way, we are also sending our own fossils into the future. Every photon reflected from your face, every radio wave that escapes into space, every signal we send to our spacecraft, they're all moving outward, carrying an image of us. Long after our world changes, long after our sun burns out, those little messengers will still be traveling, telling some distant observer, "We were here." So the next time you stand under a clear sky, try this. Pick a star, any star, and hold its light in your gaze for a moment. Think about how long it has been traveling, what it has passed, how patient it has been. Then, let it remind you that you too are part of this long chain of light, both a receiver of ancient messages and a sender of new ones. The fossils of light are not relics in a museum. They're still moving, still arriving, still telling their stories. And as long as we keep looking up, we'll keep adding our own page to the story they tell. There's a moment in any friendship when the last conversation has already happened, even if neither of you knows it yet. The words you spoke that day were the final ones you would ever exchange. Maybe life drifted you apart. Maybe distance made it harder to reach each other. Maybe you simply stopped sending messages. Whatever the reason, the connection quietly faded, and the voices you once knew so well became silent. In the universe, something similar happens, not between people, but between galaxies. We've already spoken about the cosmic event horizon, that invisible boundary beyond which light can never reach us. But here's another truth. Even galaxies we can see right now are slowly, inevitably slipping away from us, and one by one, their light will stop calling our name. This is because the universe is expanding, and the expansion is accelerating. Imagine that the fabric of space is a great elastic sheet with galaxies pinned to it. As the sheet stretches, the galaxies move farther apart. But unlike pins, the galaxies aren't fixed to the sheet. They're part of the sheet itself. When the stretching speeds up enough, the space between us and a distant galaxy grows faster than the light from that galaxy can cover it. Light doesn't stop traveling. Of course, photons keep moving at their unyielding pace of about 300 learn kilometers per second. But as space expands, those photons are forced to cross a road that's lengthening under their feet. It's like trying to walk towards someone on a treadmill that's running the opposite way. At first, you make progress. Then, as the treadmill speeds up, your steps slow in relation to them. And at a certain point, no matter how fast you try to walk, or even run, you can't get closer. The distance grows, and eventually, they fade from view. The fading here isn't sudden. It's a slow stretching of light, a phenomenon known as redshift. Just as the pitch of a siren drops when an ambulance moves away from you, light waves lengthen when their source is moving away. In our accelerating universe, distant galaxies are receding so quickly that their light is stretched far beyond the visible spectrum, into infrared and eventually into wavelengths too long for our instruments to detect. When that happens, it's as if the galaxy has turned away mid-sentence. The conversation ends, not with a bang, but with a gentle dimming into silence. And because the expansion never stops, the number of galaxies whose voices we can still hear is always shrinking. Billions of years from now, the night sky will be far emptier than it is today. Our own Milky Way and its nearest companions will remain, bound together by gravity, but the rest of the cosmos will fade into invisibility. There's a bittersweetness in that thought. We are alive in a fortunate age, when the universe is still full of messages for us to receive. We can see across tens of billions of light years, gather the ancient light of galaxies that may have already transformed or vanished. We can map their shapes, measure their movements, and imagine their stories. We can still hear their voices calling across the deep. I sometimes imagine those voices as songs. Some are bright and clear, carrying the energy of newborn stars. Others are low and faint, the echoes of galaxies in their quiet twilight years. Each one is unique, shaped by the history of its stars, the dance of its planets, the subtle pull of its neighbors. Together, they weave a chorus that has been playing since the dawn of time. But the chorus is changing. The higher notes, the ones from the most distant galaxies, are slipping lower and lower until they vanish into a register we can no longer hear. It's not that they've stopped singing. It's that the stage between us is widening too fast, stretching the music until it's too deep for our ears. The concert continues, but our seat in the audience is growing farther from the stage. That thought could feel hopeless, but I think there's a kind of grace in it too. Knowing that the universe will one day be quieter makes me want to listen more carefully now. It makes me want to point a telescope toward a faint smudge in the sky and spend hours gathering its light, even if that smudge is just a whisper in the dark. It makes me want to remember that every photon we catch is a victory against time and distance, a note that made it through before the silence arrived. And perhaps, when the last voices fade, we will still have our own to send out. Our light, our radio signals, our pulses of laser beams. These will travel outward, crossing galaxies that have already stopped speaking to us, in some far-off place, perhaps in another bubble of an observable universe. Our message might arrive, faint and red-shifted, but still carrying the echo of our existence. When light stops calling our name, it doesn't erase what was said. The messages we've received remain written in the starlight we've stored, in the maps we've made, in the stories we've told. We will still have the fossils of light we spoke about before, the preserved moments of a brighter, fuller sky. And maybe that's enough. Maybe the beauty of the night isn't just in what we can see now, but in the knowledge that we are here, in this particular moment, when the universe is still generous with its light. So tonight, while the sky is still full, go outside if you can. Look at the faintest star you can find, the one you have to squint to see. Know that it's not just a point of light. It's a voice from the past, calling across the widening space, still reaching you for now. And someday, when it no longer can, you'll remember the time when it did. If you've ever baked bread, you know the quiet anticipation that comes with waiting for dough to rise. There's something almost magical about it. You start with a dense, small lump, and over time, it swells and stretches, changing texture and shape, taking on the promise of something new. You can't rush it. The yeast will work at its own pace, invisible but unstoppable. Now, imagine that dough as the very fabric of our universe, and the raisins inside as galaxies. This is one of the simplest, yet most powerful analogies for cosmic expansion, the raisin bread universe. Let's picture it together. You're in a warm kitchen. A loaf of dough sits before you, scattered with raisins. Right now, the raisins are relatively close. You could measure the distance between any two and find that it's only a few centimeters. But as the dough rises, stretched by the action of yeast, every raisin begins to drift farther from every other raisin. Not because the raisins are moving through the dough, but because the dough itself is expanding, carrying them with it. This is what's happening in our universe. Galaxies aren't flying away from some central explosion point like shrapnel from a firework. Instead, the dough of space is expanding in all directions. Every galaxy is moving away from every other galaxy, not because they're actively traveling, but because the space between them is growing. What's especially beautiful, and maybe a little mind-bending, is that there is no center to this expansion. In our bread analogy, you could point to the middle of the loaf, but in the real universe, space expands everywhere at once. From your perspective here on Earth, it looks as if every distant galaxy is moving away from you. But if you stood on a planet in a galaxy billions of light years away, you'd see the same thing. Every point sees itself as the center of its own expanding universe. The raisin bread analogy also explains why more distant galaxies recede faster. In the loaf, the farther apart two raisins are, the more dough there is between them. As the dough expands, all that space stretches, adding to their separation. Similarly, in the cosmos, the more space there is between two galaxies, the faster they appear to be moving away from each other. But here's where the analogy needs a little care. In bread, the yeast eventually stops working. The dough reaches its maximum size and goes into the oven. Our universe, as far as we know, has no oven. The expansion doesn't seem to be slowing, it's accelerating. The yeast of cosmic expansion is dark energy, and unlike yeast, it doesn't get tired. The idea that everything is drifting apart can feel lonely, even bleak. But the truth is more nuanced. While galaxies outside our gravitational neighborhood are receding, the pull of gravity still binds together smaller groups of galaxies. Our Milky Way, for example, is part of the local group, which includes Andromeda and dozens of smaller galaxies. Within this local dough, so to speak, the yeast of expansion can't overcome the stickiness of gravity. Over billions of years, some of these galaxies will even merge, becoming new, larger galaxies. Still, on the grand scale, the expansion is undeniable. And for me, the bread analogy makes it feel almost cozy. It's a reminder that the universe isn't a static, cold emptiness, but a living process. Space itself is dynamic. It grows, changes, and evolves. Even now, as you sit listening to this, the dough of the universe is stretching. Galaxies are drifting just a little farther apart. Light traveling between them is being gently pulled, its wavelengths lengthening like taffy. I sometimes imagine the cosmos as a bakery where the loaves never stop rising. New stars ignite, old stars fade, and the bread just keeps growing. We are raisins in that infinite loaf, carried along by forces we can't control or even feel directly, yet still connected to the whole. Of course, no analogy is perfect. The loaf has an edge, but our universe might not. The loaf expands into the air of the kitchen, but space doesn't need an outside to expand into. It simply stretches its own geometry. That's where the bread image stops being literal and becomes something more poetic. It's less about the mechanics and more about the feeling, the sense of being part of something that's constantly unfolding. There's a quiet reassurance in that. In our everyday lives, we often feel pressure to move, to act, to change things ourselves. But in the cosmic view, we are already in motion, even when we're standing still. We are part of the universe's slow, steady dance outward, our positions changing in ways that only make sense across billions of years. So, if you ever feel small or insignificant, remember the bread. Remember that even the tiniest raisin shares in the journey, carried by the same currents as the grandest galaxy. You don't have to push or strain. You are already part of the story, just by existing. And maybe, the next time you smell bread baking, you'll think about galaxies floating in warm, invisible dough, drifting apart but still part of a single, shared loaf. You'll remember that expansion is not just a scientific fact, it's a metaphor for life itself. We grow, we drift, we change shape. The spaces between us widen, but the shared origin remains. We all began in the same hot, dense dough of the early universe, and no amount of stretching can erase that. Some nights, I imagine the whole cosmos breathing. Each galaxy is a grain in the lung of infinity, expanding with every inhale. And maybe one day, far beyond our ability to measure, there will be an exhale. But for now, the breath continues, and we are caught in the gentle tide of it, rising with the loaf, our place in the vast recipe secure. Illustration ideas. A loaf of bread mid-rise, with raisins drifting farther apart, overlaid with tiny galaxy shapes instead of raisins. A view of space as a soft, glowing dough expanding in all directions, carrying galaxies like raisins embedded in its fabric. If you've ever walked in thick fog, you know how disorienting it can be. The world loses its straight lines. A road that you thought was level seems to tilt. Trees emerge at odd angles. You begin to wonder whether you're walking in a straight path at all, or if you've been slowly curving without noticing. The universe is like that, only on a scale so vast it's almost impossible to imagine. From our small vantage point, it's tempting to think of space as flat and infinite, stretching endlessly in all directions. But the truth is, the shape of the universe may be far more interesting and far less intuitive. In cosmology, we talk about three broad possibilities for the universe's shape: flat, open, or closed. A flat universe is like an infinite sheet of paper, no curves, no loops, just unending two-dimensional surface in every direction. An open universe is like a saddle, curving outward so that parallel lines eventually diverge. A closed universe is like the surface of a sphere, finite, but without edges. If you travel far enough in one direction in a closed universe, you could, in theory, return to where you started. This idea, that you might loop back on yourself without ever hitting a wall, feels almost magical. You could set off into the night sky, charting a straight course past galaxies and quasars, past cosmic dust and clusters, past even the edge of the observable universe. And if space were curved in just the right way, your path would eventually carry you back home. It's a bit like walking on Earth. You can go north, south, east, or west for as long as you want, but you'll never fall off an edge. You'll just keep looping around a curved surface, bound by the planet's geometry. Only in space, the curve wouldn't be something you could see. It would be woven into the fabric of the universe itself. We know that massive objects like stars and black holes can bend the path of light, a phenomenon known as gravitational lensing. This happens because they curve the spacetime around them. But what if the universe as a whole has curvature? That curvature would be far more subtle, spread out across unimaginable distances. Detecting it requires incredibly precise measurements of things like the cosmic microwave background, the ancient light we talked about before, and the distribution of galaxies across space. Right now, the best evidence suggests our universe is very, very close to flat. But close to flat doesn't mean perfectly flat. It could be slightly curved, in ways we haven't yet detected. And even if it is perfectly flat, that doesn't necessarily make it infinite. It could still have a topology that loops back on itself, like a video game map where going off one edge makes you reappear on the other side. When I think about this, I'm reminded of sailing on an open sea. You stand at the bow of the ship, staring at the horizon, and it looks flat. The water stretches out in a perfect, level line. But that's just because your eyes can't see the curve of the earth from where you are. Give it enough distance, and the curve becomes real. Ships disappear hull first over the horizon, and a globe's roundness reveals itself. Maybe the universe is the same way. From our tiny corner, it feels flat, but across its true scale, a curve might be quietly guiding our path. And if space does loop back on itself, there's a strange implication. Light could, in theory, circle the universe and return to us from the opposite direction. If we looked far enough, we might see an ancient, distorted version of our own galaxy, sent on a long journey around the cosmic loop. We wouldn't recognize it. It would be billions of years younger, perhaps with a different shape, but it would be a reflection of us, a ghost in the geometry of the universe. The possibility that the cosmos could be both finite and edgeless is one of my favorite concepts in science. It defies our instinct to think of things as having a clear boundary. We like edges, fences, shorelines, the final page of a book. But space doesn't have to follow our preferences. It could be whole without being endless, bound without being bordered. Of course, there's also the possibility that space really is infinite, stretching forever without looping back. In that case, there would be no edges, no boundaries, and no returning to where you began. You could travel for eternity and never see the same galaxy twice. The thought is dizzying, but also strangely freeing. Whether flat, open, or closed, the shape of the universe isn't just a mathematical curiosity, it tells us something about its past and its future. A closed universe might one day stop expanding and collapse back in on itself, a big crunch. An open universe might expand forever, cooling and thinning until stars burn out and only darkness remains. A flat universe might balance delicately between those fates, its destiny shaped by the elusive dark energy we still barely understand. Standing under the night sky, these possibilities feel less like abstract physics and more like different moods of the cosmos. A closed universe is a story that circles back to its beginning. An open one is a story that wanders endlessly. A flat one is a story stretched taut, a balance between return and escape. And you, here, now, are part of whichever story is true. You are a character written into the shape of everything, moving along a path determined not just by where you are, but by the geometry of space itself. Whether that path is a loop or an infinite stretch, you are walking it every second, carried along by a curve you can't feel but that shapes every step. From the time we're children, we're taught to see the world in boundaries, the edge of the table, the end of the road, the last page of a book. Even our maps have neat borders, with countries outlined in crisp lines of ink, as if the land itself agrees with the divisions we've drawn. There's a comfort in this. Boundaries tell us where things stop, and where other things begin. They make the world feel understandable, containable. So when we look up at the night sky, it's natural to ask, where does it end? Surely there must be a wall somewhere, a final horizon where space stops and something else begins. Maybe a black curtain, maybe a shimmering shell, maybe, as some ancient myths imagined, a ring of fire or an ocean beyond which no ship can sail. But the universe, it seems, does not care for our love of edges. Space doesn't need them in the way a table or a map does. You can have a finite space without a border, just as you can have a sphere without a corner. You can also have an infinite space that stretches forever without a single boundary to mark its extent. Part of the illusion of an edge comes from how we experience the world. On Earth, we're used to being surrounded by solid objects, walls, fences, mountain ridges that block our way. When we encounter open space, we measure it in terms of how far we can travel before something stops us. In space, the only things that can stop you are the limits of time, energy, and the speed of light. There's no cosmic brick wall waiting out there. If the universe is infinite, you could, in theory, keep going forever. And if it's finite but edgeless, you could keep going and eventually return to where you started, never once encountering a cliff to fall from. I like to think of it as walking on the surface of Earth in the age before we knew it was round. You could walk in one direction for months, years, your surroundings changing constantly. To you, it would feel like a straight path with no end. The concept of looping back without ever hitting a wall might feel absurd, until one day you find yourself approaching your own home from the opposite direction. The edge you imagined turns out to be an illusion, born from not yet seeing the whole picture. In cosmology, the absence of an edge is deeply tied to the shape and topology of space, which we explored in Part 7. But there's also a psychological element. We are edge-seeking creatures. Edges give us closure. An unbounded universe is unsettling precisely because it denies us that closure. We want to know where the outside is, what lies beyond. But beyond space is a tricky idea, because space is not an object floating in something else. It is the framework for where and when everything happens. If space itself has a limit, what would be on the other side? The question assumes there must be a place beyond space. But that's a bit like asking what's north of the North Pole. The concept doesn't quite fit. Of course, humans have always imagined what might lie past the edges of our world. In ancient maps, unexplored regions were sometimes labeled, "Here be dragons," a warning that beyond this point lay mystery and danger. Our cosmic maps, in a way, still have such labels, only now they read beyond observable universe. It's not danger we expect, but uncertainty. The dragons have been replaced by question marks. The illusion of an edge is also strengthened by how we see the observable universe. We imagine the bubble we talked about in Part 2 as if it were a snow globe, clear, spherical, containing everything, with a clean surface beyond which there's nothing. But that surface isn't a real barrier. It's just the limit of what light has had time to reach us. Beyond it, the universe, if our theories are right, goes on. Maybe forever, maybe curving back on itself, but not stopping in the way a wall stops you. There's another analogy I like here. Imagine floating in a dense fog on a calm sea. Your vision is limited to a perfect circle around you, but you know the ocean doesn't end at the fog's edge. The boundary is just the limit of your perception. The water continues, quietly, invisibly, without concern for whether you can see it. I sometimes wonder if our longing for an edge is also a longing for answers. An edge feels like a conclusion, a place where you can say, "Here is the final fact." An infinite or edgeless universe refuses to give us that. It says, "There's always more." and leaves us with questions that multiply instead of resolve. That can be uncomfortable, but it can also be liberating. Without an edge, there is no ultimate stopping point for curiosity. And maybe that's the gift of the illusion. It gets us looking. We build telescopes, launch probes, map the heavens, all in the hope of finding the limit. And along the way, even if the edge never appears, we discover wonders we couldn't have imagined. The search itself becomes the reward. So perhaps the answer to where is the edge of space is, it's in our minds. It's the point where our understanding stops, for now. And as our understanding grows, the edge recedes, not because space has changed, but because we've pushed back the boundaries of our own knowledge. The universe doesn't end at the edge of our map. It keeps going, in whatever shape it has chosen, quietly indifferent to whether we've drawn its outline yet. And maybe that's all right. Maybe the beauty of the cosmos is that it's big enough to hold both our maps and all the blank space beyond them. Sometimes, when I walk through an old house, I wonder about the rooms I can't see. The hallway might turn a corner, leading to a door I haven't opened yet. From where I stand, it seems like the whole world is just the room I'm in, but I know, deep down, that there's more. For some scientists, the universe feels like that. We live in one room, vast beyond our comprehension, decorated with stars and galaxies instead of furniture, but perhaps it's only one chamber in a much larger structure. The idea that there might be other rooms is called the multiverse hypothesis. Now, multiverse can mean a few different things, depending on which scientist you ask. In one version, our universe is just one bubble among countless others, each with its own space-time, its own laws of physics, maybe even its own kinds of matter. These bubbles could be scattered through an even larger cosmic foam, forever isolated from each other. In another version, the multiverse isn't separate bubbles in space, it's separate outcomes in time, each one branching off whenever a quantum event can go more than one way. That's the many worlds interpretation of quantum mechanics. Then there are mathematical multiverse ideas, where every consistent mathematical structure exists as its own physical reality. It's dizzying, isn't it? Our own universe is already more than enough to stretch the mind, and now we're imagining more of them, each potentially infinite in size and complexity. The bubble universe idea is particularly easy to picture. Imagine a pot of boiling water. As the water boils, bubbles form and grow. Each bubble is a universe, with its own interior space. The water between them is not something we can visit. It might be a higher dimensional space that our three-dimensional minds can't really grasp. We live inside one bubble, and our observable universe is just a patch on its inner surface. Somewhere, far beyond our horizon, other bubbles might be expanding too, each with its own history, chemistry, and maybe its own creatures wondering if they're alone. If that sounds far-fetched, remember, the laws of physics as we know them don't forbid it. In fact, some theories, like eternal inflation, almost demand it. Inflation is the idea that in the earliest fraction of a second after the Big Bang, space expanded faster than light. In eternal inflation, that process never truly stops everywhere at once. Pockets of space finish inflating and become universes like ours, while other regions keep inflating, spawning new universes in an endless chain. Then there's the many worlds idea, which is stranger still. In this view, every time a quantum particle has multiple possible outcomes, the universe splits. You take one path, and somewhere else, though not in any elsewhere you could travel to, another version of you takes the other path. Every decision, every roll of the cosmic dice creates a branching set of realities, all equally real. It's less like a house with separate rooms and more like a forest where every fork in the path is taken and every possible walk exists in parallel. I'll admit, part of me loves the multiverse idea, and part of me resists it. It's thrilling to think that our universe might be just one among countless others, each with its own strange beauty. But it's also humbling, maybe even unsettling, to imagine that the cosmos we know, with all its galaxies and histories, might be only a tiny fraction of what reality contains. And there's the practical problem. How could we ever know? If other universes are completely cut off from ours, no shared space, no shared time, then no light or signal from them could ever reach us. They would be beyond even the most generous definition of observable. It would be like living in a soundproof room, wondering if there are other voices in the building. You could suspect it, even reason it out, but you could never hear them. Some physicists hope for indirect clues, subtle imprints left on our universe by collisions with other bubbles in the distant past, or strange patterns in the cosmic microwave background that might hint at influences from outside. But so far, the evidence is thin. The multiverse remains, for now, in the realm of speculation, a mathematical and philosophical playground where the possibilities are endless. That doesn't mean it's meaningless. Thinking about the multiverse stretches our imagination, forcing us to confront how limited our viewpoint really is. It reminds us that reality may be far bigger, stranger, and more layered than we can see. And even if the multiverse is never proven, the very act of imagining it changes how we see our own universe. I sometimes picture it like standing in a darkened theater. The spotlight is on our stage, the only one we can see. But maybe, beyond the edges of the light, there are other stages, each with its own actors, each telling its own story. We can't watch those plays, but knowing they might exist makes our own performance feel both smaller and more precious. If there is a multiverse, then somewhere out there, though out there is a poor choice of words, might be a universe almost identical to ours, except that in that reality, you're listening to this in a different room, or wearing a different sweater, or sipping tea instead of coffee. And somewhere else, there might be a universe where galaxies are made of glowing mist instead of stars, where physics dances to a rhythm we can't imagine. We may never walk the hallways between these rooms, but that doesn't mean we can't stand at our own doorway, peer into the dark, and wonder. After all, much of human progress has come from looking into the unknown and saying, I don't know what's there, but I want to find out. The multiverse might be unreachable, it might be unprovable, but it is also a reminder that our story may not be the only story, that the reality we see might be just one verse in a much longer, stranger song. Sometimes, late at night, I like to imagine the universe as something more than stillness and expansion. We often picture space as calm, a silent stage where galaxies drift apart, their movements guided only by the quiet stretch of cosmic expansion. But what if the whole stage was turning? What if the fabric of reality itself was slowly rotating, carrying everything with it in an endless cosmic swirl? This is not just poetic fancy. In 1949, the mathematician Kurt Gödel, best known for his incompleteness theorems in mathematics, came up with a strange solution to Einstein's equations of general relativity. His model described a rotating universe, one in which space-time itself spins. In Gödel's cosmos, you could, in principle, take a journey that loops back in time, returning not just to the same place, but to the same moment. The idea of closed time-like curves, paths that bring you back to your own past, emerges naturally from such a rotation. It's a dizzying concept. In our day-to-day lives, time feels like a river that only flows one way. The idea that the river could circle back on itself, letting you step into your own footprints from yesterday, feels like a paradox. And yet, Gödel's equations say it's mathematically possible, at least in theory. Of course, the evidence suggests that our actual universe doesn't rotate in this way, or at least not enough for us to notice. If space-time were spinning significantly, we'd expect to see subtle patterns in the motion of galaxies and in the cosmic microwave background. So far, the data points toward a universe without a global spin. Still, the fact that the equations allow it is a reminder. Reality might be far stranger than the version we're familiar with. And Gödel's rotating universe is just one of many exotic possibilities. Some models propose that the universe could be shaped in unusual ways, like a three-dimensional version of a Mobius strip, where traveling far enough would flip you back into a mirror version of yourself. Others imagine cosmic domain walls, vast boundaries separating regions of space with slightly different physical laws, as if the universe were divided into neighborhoods, each with its own rules. Crossing one might mean entering a place where the speed of light is different, or where gravity pulls just a little stronger. There's also the idea of bubble collisions, if the multiverse exists, and other universes are bubbles expanding in a cosmic foam. Then, once in a while, two bubbles might collide. The imprint of such a collision could be visible in our sky as an odd, circular pattern in the microwave background, like a faint bruise on the fabric of space-time. Some researchers have even hunted for such patterns, though so far nothing definitive has been found. Then there are theories where the constants of nature aren't constant at all. Imagine a universe where the fine structure constant, an unchanging number in our physics textbooks, drifts slowly over time. The speed of light might shift, the strengths of forces might waver. Over billions of years, the very foundation of chemistry and physics could subtly retune itself. We like to think of the laws of physics as immutable, but what if they're more like the weather, stable for long stretches, but capable of slow, dramatic change? Some of the strangest models are born from trying to reconcile quantum mechanics and gravity. In these ideas, the structure of spacetime might be granular at the smallest scales, like a woven fabric whose individual threads are too fine to see with the naked eye. At the Planck length, so small it defies direct comprehension, space itself might fizz and foam, with tiny wormholes opening and closing, brief connections between distant points in the cosmos. Most of them would be too fleeting or too small for anything to pass through, but in principle, such a network could knit the universe together in hidden ways. When I think about these possibilities, I picture the universe as an immense, locked room, and science as a set of keys we've been slowly collecting. So far, we've found keys that open small doors, revealing galaxies, atoms, the laws of motion. But every now and then, we find a key that doesn't seem to match any lock we know. That's what Gödel's universe feels like to me. A strange key that opens a door to a room we're not sure exists. It's tempting to dismiss these exotic models as fantasy. After all, why dwell on possibilities we may never prove? But I think they serve an important purpose. They remind us that the reality we experience is not the only reality that mathematics can describe. They push the boundaries of what we're willing to imagine, and sometimes, in doing so, they prepare us for surprises nature has yet to reveal. And maybe, just maybe, the universe is saving some of these surprises for us. A subtle twist in space-time, a hidden pattern in the sky, a quiet sign that the stage is not as still as we thought. So tonight, as you drift toward sleep, picture yourself floating in a slow, gentle whirl, as if the stars themselves were turning around you in a vast, patient spiral. Whether or not the real universe rotates, the thought is comforting, a reminder that we are carried along by something larger than ourselves, part of a motion we can't fully feel, but that still shapes our path. We tend to think of the laws of physics the way we think of the rules of a well-made game: stable, unchanging, agreed upon by all the players. Gravity always pulls, light always travels at the same speed. The charge of an electron is always the same number, carried faithfully from atom to atom, century to century. These rules are the scaffolding of the cosmos. Without them, the whole structure would seem to sway. But what if the rules themselves could change? It's not such an impossible thought. In our everyday lives, we're surrounded by systems whose rules shift over time. The climate changes, economies evolve, even the human body, bound by biology, transforms with age. We tend to assume that the universe is more constant than these familiar systems, but nature has a way of surprising us. Physicists sometimes speculate that the so-called constants of nature might not be perfectly constant after all. The fine structure constant, for example, a number that defines how strongly light interacts with matter, might drift, ever so slightly, over billions of years. If that number changed enough, atoms themselves would alter, chemistry would rewrite itself, and the familiar periodic table might become something unrecognizable. Then there's the speed of light. It's treated as the ultimate speed limit, and all our modern physics is built around it. But in some early universe models, light may have traveled faster, much faster, during the first moments after the Big Bang. This could help explain why the cosmos is so uniform on large scales, even though distant regions should have been too far apart to exchange information. In such a scenario, the rules weren't rewritten, they were still being written. The possibility of changing laws extends beyond time. It might stretch across space as well. Some theories propose that different regions of the universe could have slightly different physical constants, as if the cosmos were divided into districts, each with its own local rules. In a distant corner of reality, gravity might be a little stronger, or the electron's charge might be slightly different. The changes could be small enough that life still forms, but perhaps very different kinds of life. These differences might be hidden from us not by walls or barriers, but simply by distance and time. If the laws in those regions are different enough, the light they emit might not look like any light we know, or maybe those regions are so far away that their signals will never reach us, forever sealed in their own chapters of reality. I sometimes picture the universe as a giant quilt. Each patch follows its own subtle pattern, stitched together with others to make a whole. From up close, you can only see your own patch and maybe the ones next to it. Step back far enough, if you could, and you'd see the patchwork, each piece distinct, yet part of one fabric. If the laws of physics can vary, then the question, does space have an edge, becomes more complicated. The edge might not be a physical boundary, but a change in the very rules themselves, a place where crossing over feels less like stepping past a wall and more like stepping into another game entirely. You'd still be playing, but the pieces would move differently, and the board might not be recognizable. It's an unsettling thought, but also an intriguing one. It suggests that there are edges we can't see until we reach them, not edges in space, but edges in kind. And it raises another question. If the rules can change, what anchors reality? Is there something deeper, more fundamental, that remains constant no matter the setting? Or is reality, at its core, a shifting thing, reshaping itself in ways we have yet to imagine? Some physicists search for a theory of everything, a single framework that explains all forces and particles in the universe. If they find it, maybe it will show us why the constants have the values they do, and whether those values could have been different. Others suspect that the values are simply accidents of cosmic history, random outcomes in a much larger set of possibilities, perhaps set during the birth of our universe. In that case, different universes, or even different regions of our own, might play by different versions of the same cosmic tune. The thought of changing rules makes me feel small, but not powerless. Small, because it reminds me that even the things we take as unshakable might be part of a larger, shifting story. Not powerless, because it tells me that discovery is never finished. Even if we think we know the rules, we might only know them for here and now. Tomorrow, or 10 billion years from now, there might be more to learn. And perhaps, just perhaps, this is one of the universe's quiet kindnesses. By letting the rules be so stable in our era, it has given us the time and the stability to learn them. If gravity were changing dramatically from year to year, or if the charge of the electron drifted wildly in a human lifetime, we might never have built the sciences we have. The rules have stayed put long enough for us to read them. Now, the challenge is to find out whether they've always been this way. So tonight, as you rest under the steady pull of gravity, breathing air whose chemistry has been unchanged for eons, imagine the possibility that somewhere, far away, or long ago, the game was different. Imagine worlds shaped by other rules, where stars burn cooler or hotter, where matter itself has different textures. And imagine stepping into those places, feeling the shift in the air, realizing that you are still in the universe, just not the same one you knew before. We've been speaking about space as if it's the only stage on which the universe performs, but space is only half the story. The other half is time. And here's the strange thing. Just as space might have no edge, time may have one. Not a cliff or a wall, but a beginning. A moment when it first began to tick. In our daily lives, beginnings feel natural. Every story starts somewhere. There's the first page of a book, the first scene of a film, the first heartbeat of a child. Even our days have a clean division. The sun rises, and a new day begins. So it feels intuitive to ask, what happened before the universe began? What was there before the Big Bang? But in physics, that question may not make sense. The Big Bang wasn't an explosion in space. It was the expansion of space itself, and with it, the birth of time. Asking what happened before the Big Bang is like asking what's north of the North Pole. It's a question built from concepts that don't apply. Before is a word that belongs to time, and time itself may have started in that moment. For the first fraction of a second, the universe was a hot, dense, blindingly bright place. Energy boiled in every direction. Space expanded at an incredible rate, in a phase we call inflation. In that moment, not only were all the galaxies, stars, and planets compressed into a tiny seed of space-time, so was the very potential for before and after. It's humbling to realize that the smooth flow of seconds we take for granted is not eternal. Time itself had a birth. The ticking of the cosmic clock began when the universe did, and that clock has been running ever since, keeping pace with the expansion of space. But that doesn't mean the idea of before has no place in our imagination. Some theories suggest that the Big Bang might not have been the absolute beginning, but rather a transition. In these scenarios, our universe could be one cycle in a repeating pattern. Expansion followed by contraction, followed by another expansion, a cosmic heartbeat across eons. If that's true, then before our universe was simply another universe, perhaps with different stars, different galaxies, maybe even different versions of physical laws. Other models imagine that our Big Bang was just one bubble forming in a larger multiverse, as we discussed earlier. In that case, before might be like asking what happened before a particular bubble rose to the surface of boiling water. There may have been countless others forming and rising alongside it. Then there are more speculative ideas still. that time itself might be an emergent property, something that arises from deeper laws of physics, and that, in some ultimate sense, the universe exists outside of time entirely. If that's the case, our experience of past, present, and future could be like walking through the frames of a film. The whole reel already exists, but we only see one frame at a time. Whatever the case, we are bound to our own slice of time. We can remember what came before us, and we can imagine what may come after, but we cannot step outside the flow. And that flow has a direction, the arrow of time, that points from order toward disorder, from past toward future. This arrow is tied to the universe's expansion. If the universe were to stop expanding and collapse in on itself, the arrow might change, and time as we know it could behave in ways we can hardly picture. Thinking about the edge of time changes how I think about the edge of space. If space has no clear border, but time had a beginning, then the truest boundary of our universe might not be out there among the stars, but back there, at the start of everything. It's not a place we can travel to. It's a moment we can never revisit, but whose effects are still unfolding around us. The light from the Big Bang still glows faintly in every direction, stretched into microwaves by billions of years of expansion. That light is the oldest messenger we have, a silent reminder of time's first breath. When I look at maps of the cosmic microwave background, I feel a strange intimacy, as though I'm looking at the universe's baby photo, except this baby contains everything that has ever been and ever will be. Of course, the human mind wants to go further. If time had a beginning, what caused it? If there was nothing before, how did something begin at all? These are the questions where physics brushes up against philosophy, where equations can take us only so far. Beyond that, we are left with wonder, speculation, and perhaps a little humility. Maybe there was never nothing in the way we imagine it. Maybe nothing is simply the absence of the things we know how to measure, while deeper realities hum quietly beneath, giving rise to space and time when conditions are right. Or maybe beginning is just a feature of our particular universe, and in a larger reality, there is no start or end, only transformation. Either way, the beginning of time is as close to an edge as the universe has ever offered us. We can't see past it, we can't touch it, but everything we are flows from it. And perhaps that's the most profound kind of boundary. One that's not a limit on where we can go, but a limit on what we can know. So tonight, if you find yourself staring into the darkness between the stars, remember that you are also looking backward in time. Each photon that reaches you is a marker along the trail from now to then. Follow them far enough, and you arrive at a moment when the first light broke free, and the universe began to grow. Follow them further still, and the path ends, not in a wall, but in the silent mystery of the first instant, where time itself took its first step. Close your eyes for a moment and imagine a world without light, not just night on Earth, where the stars still glimmer and the moon still paints silver paths across the water, but a darkness so deep and complete that there is no up, no down, no near, no far. A universe without form, without horizon, without anything for your eyes to hold on to. That was the cosmos in its earliest days. After the Big Bang, for hundreds of thousands of years, light could not travel freely. The universe was filled with a hot, dense fog of particles, electrons, protons, and photons constantly colliding. Any beam of light that tried to cross this young cosmos was scattered almost instantly, bounced around like a voice in an echo chamber so full that no single word could be heard. It was an opaque place, a cosmic womb where the seeds of everything were gestating. But as the universe expanded, it cooled. Protons and electrons began to combine into neutral atoms, mostly hydrogen and helium. This period, called recombination, happened when the universe was about 380 Ionosaturn years old. Suddenly, light was free to travel, no longer trapped in the fog. This moment released the cosmic microwave background, CMB, the oldest light we can still detect today. If we could somehow stand in that moment, the whole sky would blaze with a uniform golden glow. But over the eons, as the universe expanded, that light stretched into microwaves, invisible to our eyes but detectable with sensitive instruments. It's everywhere, all around you right now, passing through the room you're in. A faint whisper from a time when the universe was still a child. The CMB is more than just a beautiful relic. It's a map. When scientists measure it, they find tiny temperature differences, minute fluctuations that show where matter in the early universe was slightly denser. These small variations acted like the first fingerprints of cosmic structure. Over billions of years, gravity pulled the denser regions into stars, galaxies, and eventually, the great cosmic web of matter we see today. But the story of the first light doesn't end there. After recombination, the universe entered what we call the cosmic dark ages. There was light, yes, but it was the ancient glow of the CMB, gradually dimming with expansion. No stars yet, no galaxies. Just clouds of hydrogen and helium drifting in the darkness, waiting for gravity to do its slow, patient work. It would take hundreds of millions of years before the first stars were born. These were not like the stars we see now. They were giants, massive, hot, and short-lived, burning their fuel in just a few million years before exploding as supernovae. Their light pierced the darkness, and their death scattered heavier elements, carbon, oxygen, iron, into the cosmos, elements that would later form planets, oceans, and eventually, us. This era, when the first stars ignited, is called the cosmic dawn. The light from these stars began to ionize the hydrogen in the universe, clearing away the last of the cosmic fog. Slowly, the darkness gave way to the first galaxies, the first clusters, the beginnings of the night sky as we know it. The James Webb Space Telescope, JWST, is now peering into this era, looking back over 13 billion years to capture the faint glow of these early structures. Every image it sends is like a time capsule, a glimpse into the moment when the universe was still waking up. Seeing these ancient galaxies is like looking at the first campfires lit in a vast wilderness, a reminder that even in the greatest darkness, light finds a way to emerge. I often think about how patient the universe had to be. Nearly 400 equal years just to let the first light travel freely. Hundreds of millions more before stars painted the darkness with their brilliance. If you measure cosmic time on a human scale, it's as if the universe spent most of its youth in silence, only speaking its first words when it was already middle-aged. And yet, those first words shaped everything that followed. Without the CMB, we wouldn't know how the cosmic stage was set. Without the first stars, there would be no heavy elements to make planets, no chemistry to make oceans, no life to wonder about it all. When I stand under the night sky, I like to think of it as a layered memory. The bright stars we see are recent arrivals in cosmic history. Behind them lies the faint light of galaxies billions of years old. And behind those, still reaching us even now, is the ancient whisper of the CMB, the echo of the moment light first broke free. The phrase cosmic dawn feels poetic, but it's also accurate. Like the Earth at sunrise, the universe went from darkness to a slow, spreading glow, and just like a dawn, it wasn't a single instant, but a gradual brightening, wave after wave of light touching the cosmic landscape. Somewhere out there, light from the very first stars is still traveling toward us, crossing gulfs of time and space. One day, perhaps, our instruments will catch it. When we do, we'll be seeing not just the birth of stars, but the birth of starlight itself, the moment the universe began to illuminate its own story. When we think of light, we tend to imagine what our eyes can see: the golden warmth of sunlight spilling through a window, the cool silver of moonlight on a quiet street, the scatter of stars on a clear night. But these are just the notes we can hear in a much larger cosmic symphony. Most of the universe's light is hidden from us, not gone, not silent, just playing in registers our eyes were never tuned to hear. Human vision is a narrow slice of the electromagnetic spectrum, the full range of light's wavelengths. Beyond the reds we see lies the infrared, warmth made visible if you have the right sensors. Beyond the violets lies ultraviolet light, invisible to us but seen by butterflies and bees. Keep going, and you find X-rays, gamma rays, radio waves, each carrying stories from different corners of the cosmos. The universe is filled with this hidden light. In fact, if you could somehow see it all at once, the night sky would blaze not just with stars, but with clouds of glowing dust, with the faint outlines of galaxies shrouded in darkness, with the silent hum of microwaves left over from the birth of everything. The empty parts of space would no longer be empty. They'd be alive with color and structure far beyond the visible rainbow. Some of this hidden light is ancient, older than the Earth itself. The cosmic microwave background we spoke of in Part 13 is one example, a bath of invisible light that fills all of space, a whisper from when the universe was less than 500,000 years old. We can't see it with our eyes, but sensitive detectors can, and when they map it, they reveal patterns that are like the DNA of the cosmos, the seed points from which all galaxies grew. Other kinds of hidden light tell stories from more recent times. Infrared light can pass through dust clouds that block visible starlight, revealing the birthplaces of new stars. Radio waves can trace the vast arms of galaxies, outlining their structure like ink in an invisible blueprint. X-rays pour from the regions around black holes, marking places where matter falls inward so violently that it heats to millions of degrees. What I love about hidden light is how it changes our relationship with the sky. When you look up with just your eyes, you're seeing a curated version of reality, as if the cosmos were choosing which parts to show you. But when astronomers build instruments to see in other wavelengths, they're like guests slipping backstage, finding that there's a whole other world behind the curtain. The shadows of the past are hidden here too. Light can be absorbed, scattered, or bent on its journey. Sometimes, it's delayed by detours through curved space-time, arriving years or centuries after it should have. In gravitational lensing, massive objects like galaxy clusters bend light from more distant sources, magnifying them and sometimes creating multiple images of the same object. We see these echoes side by side, snapshots from slightly different times, as if space itself were showing us before and after photos. And then there's light we will never see, not because it's too faint, but because it has been lost to us forever. Some photons are swallowed by black holes, their journeys ending in darkness. Others are stretched by the expansion of the universe into wavelengths so long that no conceivable detector could catch them. The further a galaxy is from us, the more its light is redshifted until it vanishes beyond our reach. These are the voices of the past that fade into silence, stories half told, chapters we can only guess at. I sometimes imagine this hidden light as a kind of ghost library. Each wavelength is a different wing, each photon a letter or page, and the universe is the author. We've learned to read some of the languages: visible light, radio, X-ray, but most of the collection is still closed to us. We can glimpse its covers, feel the weight of it, but the contents remain a mystery. In this way, the shadows of the past are not just absences, they're invitations. Every new telescope, every new detector we build is like opening another shelf in that library. The James Webb Space Telescope, for instance, is tuned to infrared, letting us see through the dusty veils of stellar nurseries and look further back in time than ever before. Radio telescopes stitch together views of the cold hydrogen that still drifts between galaxies, a remnant from the early universe. X-ray observatories peer into the furious hearts of galaxy clusters, where hot gas outshines all the stars combined. But even with all this, there's more hidden light than we'll ever recover. And maybe that's all right. Maybe part of the beauty of the universe is that it keeps some of its colors for itself. Just as a storyteller leaves certain details unsaid, the cosmos may never reveal all of its spectrum to us. When I think about the question, does space have an edge? I realize that hidden light changes the way I frame it. The edges I imagined as a child were like walls, blocking sight entirely. But in truth, the universe's boundaries are often made of light we simply can't detect. They're not walls, they're filters, hiding some of the story while letting other parts through. What we call the edge might just be the point where our vision fails. If you ever find yourself under a sky dark enough to show the Milky Way, try this. Imagine peeling back the visible stars to see the hidden light beneath. Imagine the infrared glow of dust clouds, the radio hum of hydrogen, the X-ray flare of a distant black hole. Imagine the microwave warmth from the birth of everything, still washing over you. You can't see it, but it's there. You're soaking in it right now. And maybe that's the quiet truth. We are always in the light. Even in the darkest night, we are bathed in wavelengths our eyes cannot see, surrounded by messages from across time. Space may or may not have an edge, but its light, seen and unseen, binds us to its story. When I was a child, I used to draw maps of imaginary worlds. They were simple things: pencil lines on scrap paper, outlining mountains, rivers, towns with names I made up on the spot. The borders were wherever the paper ran out. If I wanted the world to grow, I taped on another sheet and kept drawing. In a way, that's how humanity has been mapping the universe. For most of our history, the edge of our cosmic map was set not by space itself, but by the reach of our tools. First came the naked eye, limited to the sun, the moon, the planets visible to us, and the fixed background of stars. Then came the telescope, which expanded our map by orders of magnitude, the invention of radio astronomy, infrared detectors, X-ray telescopes. Each new tool was like taping on another piece of paper, extending the map into previously unseen territory. Today, our maps of the universe are vast and detailed. We have surveys that chart millions of galaxies across billions of light years. We can see great arcs of the cosmic web, where matter gathers into filaments and clusters, leaving vast empty voids in between. These structures aren't random. They are the grown-up versions of the tiny density ripples imprinted in the cosmic microwave background. From a faint, uniform glow, the universe has grown into a sprawling network of light and dark, complexity woven into every scale. One of the most remarkable projects in this grand cartography is the Sloan Digital Sky Survey. Over the course of 2 decades, Sloan has mapped the positions of millions of galaxies, turning the sky into a 3-dimensional atlas. Imagine peeling away the dome of stars above you and looking at the universe from the outside. Sloan's data lets us do something close to that, showing the cosmic web in all its tangled glory. These maps reveal something that's easy to forget. Our view of the universe is not static. Every galaxy we chart is a moment in time. The farther away it is, the older the light we see. The map is a history book as much as a geography lesson. It shows us not only where things are, but where they were, often billions of years ago. The expansion of our cosmic map also changes the way we think about the idea of an edge. In ancient times, the edge of the known world might have been the horizon over the sea. In the age of exploration, it was the farthest land seen on a voyage. Today, in astronomy, the edge is not a physical wall, but the limit of what our instruments can detect. Beyond that, the universe doesn't end. It simply fades into a realm we haven't charted yet. And yet, every time we extend our map, we run into a deeper truth. There is no single edge. The observable universe is a sphere around us, yes, but the galaxies at that edge are not special. They're just the farthest ones whose light has had time to reach us. From their point of view, we are at the edge, and from some galaxy even farther away, both of us are just points on its horizon. The map changes depending on where you stand. That realization makes our cosmic cartography feel more like a collaborative art project than a conquest. We are each mapping our own bubble of space, but the bubbles overlap, like ink stains on a growing sheet of paper. The universe, in this sense, is not something we will ever map completely, not because it's hiding, but because it is too vast for any one perspective to hold. Some of the most exciting developments in mapping aren't about galaxies at all, but about the invisible scaffolding that holds them in place. Most of the universe's matter is dark matter, stuff we can't see directly, but whose gravity shapes the motion of stars and galaxies. By observing how light bends as it passes through space, a technique called gravitational lensing, we can map this invisible matter, revealing the underlying architecture of the cosmos. These dark maps are like tracing the bones of a creature whose skin we've only just begun to see. In the years ahead, our maps will grow even more ambitious. The Vera C. Rubin Observatory, currently under construction, will scan the entire visible sky every few nights, creating a living map that changes in real time. We'll be able to track not only the slow drift of galaxies, but also the flicker of transient events, supernovae, colliding neutron stars, perhaps even the glow of something we've never seen before. And then there's the future promise of mapping using gravitational waves, the ripples in spacetime itself. Right now, we can only detect the loudest crashes in the cosmic ocean, the mergers of black holes and neutron stars. But one day, with more sensitive detectors, we might map the universe by its vibrations, listening to the shape of space as much as we look at it. When I think of all this, the maps we've made, the maps we will make, I realize that the act of mapping is not about finding an edge at all. It's about deepening our relationship with the unknown. A map is both a record of what we've seen and an invitation to go further. The blank spaces are not failures, they are possibilities. There's a quiet poetry in knowing that our cosmic maps are incomplete. Just like the old sea charts with their fanciful drawings of sea monsters, our modern maps of space have their own uncharted regions. They're just filled with galaxies instead of dragons. And maybe, when we look back centuries from now, we'll smile at the quaint incompleteness of today's atlases, just as we smile at the maps of the past. The universe will always be larger than our maps. That's not a defeat. It's a gift. It means there will always be somewhere new to point a telescope, some unmarked place where light is just now making its way to us. And when it arrives, we'll tape on another sheet of paper, draw another line, and let the map grow again. It's tempting to think of the universe as still, like a photograph, frozen in place, its galaxies scattered across space like stars painted on a dome. But the truth is, nothing is standing still. Not the planets, not the stars, not the galaxies, not even the space between them. The universe is a restless thing, always in motion. Here on Earth, we move without feeling it. The planet spins on its axis at over 600 kilometers per hour at the equator. At the same time, it orbits the Sun at about 107,000 Saturn kilometers per hour. The Sun itself is not fixed either. It orbits the center of the Milky Way, carrying our entire solar system with it at over 800,000 kilometers per hour. Even the Milky Way is on the move, drawn toward the Andromeda Galaxy in a slow-motion collision that will happen in about 4 billion years. Beyond this local dance, there is the greater choreography of the cosmos. Galaxies stream toward dense clusters, pulled by gravity's invisible hand. Whole superclusters drift toward one another. And all the while, space itself stretches, expanding in every direction. The expansion is not like objects moving apart in a static room. It's more like the room itself is growing. This means the motion we see is not just from galaxies traveling through space, but from the fabric of space itself increasing the distances between them. Light from these galaxies has to cross this expanding fabric, stretching its wavelength as it goes, which is why we see distant galaxies redshifted. Our view of the universe is a snapshot of this constant motion, but it's an old snapshot. The farther away we look, the older the light we see. So the positions of those galaxies today are not exactly where they appear in our telescopes. In a sense, every deep space image is a time-lapse photo where each dot of light is frozen in a different era. The map we hold is already out of date the moment we make it. Motion also shapes what we think of as the edge of the universe. The cosmic event horizon, which we spoke about earlier, is defined by how quickly galaxies move away from us. Some are retreating so fast, because of the expansion of space, that their light will never reach us. This is not a static edge, but a moving one. As the expansion accelerates, more galaxies slip beyond it, disappearing from our possible future view. And yet, not all motion carries things apart. Gravity works on smaller scales to pull objects together. The same cosmic forces that push galaxies away from each other also allow galaxies to merge, stars to orbit, planets to dance around suns. The universe is both expanding and binding, separating and gathering, a paradoxical motion that somehow coexists. I sometimes think of the cosmos as a grand tide. There is an outward flow, galaxies carried away by the expansion, and there are local eddies, where gravity keeps matter circling in place. We are in one of those eddies now, our local group of galaxies bound together even as the wider sea moves on. There's also the subtler, invisible motion of dark matter. We can't see it directly, but its gravity sculpts the paths of galaxies, shaping the cosmic web. In a way, dark matter is like the deep ocean currents beneath the waves, unseen but powerful, setting the rhythm for everything above. Then there's dark energy, the mysterious force accelerating the universe's expansion. If dark matter is the anchor that holds galaxies together, dark energy is the wind in the sails, pushing the cosmic sea outward faster and faster. Its nature remains one of the biggest mysteries in science, and understanding it may be the key to predicting the universe's long-term fate. All of this motion, visible and invisible, means the universe we know today is not the same one that will exist tomorrow. Over billions of years, galaxies will drift into new constellations. Star-forming regions will flare and fade. The night sky itself will change. In a far future, the stars we know will be gone, replaced by new ones, and the Milky Way will have merged into a giant elliptical galaxy with Andromeda. When I think about this, I find the idea of an edge less and less useful. In a moving universe, the edge is always changing, always defined by motion and perspective. It's like trying to mark the shoreline on a beach where the tide is rising and falling at the same time. The boundary is real, but it's never still. Perhaps the most profound part of living in a universe in motion is realizing that we are part of that movement. We are not observers standing apart. The atoms in our bodies are being carried along with the Earth's rotation, the Sun's orbit, the galaxy's drift, the expansion of space itself. Even when we feel most at rest, we are riding the great currents of the cosmos. It's strange comfort, knowing that stillness is an illusion. The universe carries us whether we move or not, and in that sense, we are never lost. We are always on the path, even if the path itself is shifting under our feet. So the next time you step outside and look up, remember that you are not simply seeing the stars. You are moving with them, part of their dance. The light you catch in your eyes is not just a picture of where they are, but a record of where they were, carried to you across billions of years in a universe that has never stopped moving. It's hard to imagine the far future of the universe. Our minds are tuned to human lifetimes, decades, maybe a century if we're lucky. Even the slow changes of mountains and rivers feel eternal to us, but the cosmos moves on timescales so vast that our lives are little more than a blink. If we want to picture the universe trillions of years from now, we have to step far outside our usual sense of time. Right now, the universe is about 13.8 billion years old. Galaxies sparkle, stars burn, planets orbit, and life, at least here, has found a foothold. But this is not a permanent stage. It's more like high noon in the day of the cosmos, a bright middle chapter. In the far future, the story will change. One of the most certain predictions we have is that the universe's expansion is accelerating. This is driven by dark energy, a mysterious force that acts like an anti-gravity on cosmic scales. As it continues, more and more galaxies will cross our cosmic event horizon, receding so quickly that their light will never reach us again. One by one, the lights at the edge will wink out, not because they've gone dark, but because the space between us has grown too quickly for their messages to cross. Astronomers predict that in a few trillion years, only the galaxies in our local group, the Milky Way, Andromeda, and their smaller companions, will remain visible. Everything else will have slipped beyond reach. Future astronomers, if there are any, will look out and see a dark, empty universe, with no sign of the great cosmic web we now map so proudly. It will be a quieter sky. The night will still hold stars, but they too are not eternal. Stars are engines, burning fuel to shine, and fuel is finite. Over time, the brightest and largest stars will burn out first, ending their lives in supernovae or collapsing into neutron stars and black holes. Smaller, cooler stars, like red dwarfs, will endure much longer, shining faintly for trillions of years. But eventually, even they will fade, leaving behind cold remnants. The far future will belong to these remnants: white dwarfs, neutron stars, and black holes. The galaxies will grow darker, their spiral arms fading like old photographs left in the sun. There's something haunting about the idea of the fading horizon, not just in space, but in time. We live in an era where the universe is both old enough to have formed rich structure and young enough to still be lit by countless stars. This is a brief and special window. In the deep future, much of the cosmic story will be invisible, lost not to destruction, but to distance and time. Black holes will dominate the far reaches of time. Some will slowly evaporate through a process called Hawking radiation, emitting tiny amounts of energy over unimaginable timescales until they vanish entirely. This process will take far longer than the current age of the universe, so long that even the word eternity feels small beside it. By then, the universe will be cold and sparse. The energy of starlight will be gone, replaced by the faint glow of fading particles and the quiet hiss of black holes dying their slow, slow deaths. Space will still exist, but it will be empty of anything we might call structure or life. And yet, this distant, dim future is not sad to me. It's part of the universe's natural cycle. Just as stars are born, shine, and die, so too will the cosmos have its bright youth, its long middle age, and its eventual twilight. The fading horizon is not a sign of failure. It's a testament to how far light can travel, how long stories can last. When I think of the far future, I picture it like the end of a great festival. The music is quieter, the lanterns are going out one by one, and the crowd has thinned. But the memory of the night lingers, and the pathways that were lit remain etched in the mind. In the same way, even as galaxies disappear from view, the universe will carry the imprint of their existence in the shape of space-time itself. From our vantage point here and now, we are lucky beyond measure. We live in a time when the sky is full of messages from across the ages. We can see billions of years into the past, connect the dots of the cosmic web, and trace the history of light from the Big Bang to today. Future observers, no matter how advanced, will never have that privilege. The information will be gone. The past will have truly slipped beyond the horizon. It makes me wonder, what are we doing with this rare gift of visibility? Are we simply collecting facts, or are we also taking the time to appreciate the beauty of the view while we have it? Knowing the horizon is fading should make each glimpse more precious, each discovery more profound. Perhaps that's the quiet lesson of the far future, that nothing in the universe is static, not even the grandest of scales. Edges shift, horizons fade, and the view changes. But that change itself is part of the wonder. When we talk about edges, we imagine sharp boundaries, like the walls of a room or the edge of a cliff. Our everyday experience teaches us that finite things have borders, but the universe does not necessarily play by these rules. One of the most surprising ideas in cosmology is that space could be finite, yet have no edges at all, curving back on itself in a way that makes every direction lead back to where you began. To get a sense of this, imagine standing on the surface of the Earth. You can walk north, south, east, or west for as long as you like. You will never fall off an edge. Eventually, if you keep going straight, you will loop all the way around to your starting point. The surface of the Earth is finite in area, but it has no border. It is a closed shape. Now, take that idea and add a dimension. Instead of the two-dimensional surface of a sphere, imagine three-dimensional space curving in a higher dimension we cannot directly perceive, just as the surface of the Earth is curved in a way that can only be fully appreciated from space. The whole of the universe could be curved in a way we can only understand through mathematics and observation. In such a universe, traveling in a perfectly straight line for long enough might, in principle, bring you back to your starting point, though the journey would be longer than the age of the cosmos itself. You would never see a wall of space. You'd just find yourself back where you began, as if the universe were a giant cosmic loop. Cosmologists describe these possibilities using the concept of topology, the study of how shapes are connected and curved. One possible topology is a closed, positively curved space, like the surface of a sphere. Another is a flat but finite shape that loops around like a video game map. Walk off one side, and you reappear on the other. In 3 dimensions, this looping can happen without any visible seam. The most famous analogy for this is the balloon universe. Imagine tiny creatures living on the surface of an inflating balloon. To them, the balloon's surface is all of space. There is no inside or outside from their perspective, just the two-dimensional skin they inhabit. As the balloon expands, every point moves away from every other. not because the creatures themselves are walking, but because the surface itself is stretching. And if they walk in a straight line for long enough, they will eventually return to their starting point. It's important to note that this analogy has limits. Our universe is not literally a balloon, and it is not expanding into some larger space. The curvature, if it exists, is intrinsic. It is built into the fabric of spacetime itself. And unlike the balloon's surface, which is two-dimensional, our space is three-dimensional, curving in a way that our minds find difficult to picture. So how would we know if the universe curves back on itself? One way would be to look for repeating patterns in the cosmic microwave background, the ancient light from the Big Bang. If space loops back, then light traveling through it might pass us more than once, arriving from different directions but carrying the same signature. Detecting such patterns would be like seeing the same landmark twice in a maze, realizing that the corridors loop. So far, the data suggests that the universe is very close to flat, meaning it might be infinite, or so large that any curvature is beyond our ability to measure. But very close to flat is not the same as definitely infinite. It leaves room for the possibility that the cosmos is a closed loop of unfathomable scale. I find this possibility deeply poetic. A looping universe would mean there is no ultimate edge, no final beyond to cross. It would mean that, on the largest scale, every journey is a circle, and everything is connected not just by gravity and light, but by the very shape of space. It also reframes what distance means. In a looping cosmos, the farthest place you could go is, in a sense, right next door. Just approached from the opposite direction. The universe becomes less like a boundless ocean and more like a great cosmic globe, where paths meet again in unexpected ways. Philosophically, a finite but boundaryless universe challenges our sense of finality. We like to think of reaching the end as a stopping point, a place where the story closes, but in a loop, there is no end, only returns. The story repeats, not in time, but in the paths light and travelers might take. I sometimes picture it as walking through a quiet forest in the fog. You move forward for hours, maybe days, and suddenly you recognize a tree, a rock, a bend in the path. You realize you have been here before, though you never turned back. That moment, the gentle shock of recognition, would be the traveler's proof that space curves. Whether or not our universe truly behaves this way remains unknown. But the idea that space could be both finite and unbounded is a reminder of how strange reality can be when we step beyond everyday intuition. It tells us that edges are not always about walls or endings. Sometimes they are about connections we can't yet see. When we ask whether space has an edge, we're really asking about the limits of reality. We imagine that beyond the last star, there might be a wall or a void, a place where space stops. But what if there is no edge because our universe is just one bubble in a vast foam of other universes? This is the realm of the multiverse, a family of theories suggesting that our cosmos may be only one of many. Each universe could have its own laws of physics, its own constants, maybe even its own dimensions. Some might be barren and dark, others filled with stars and planets, perhaps even with life. One version of this idea comes from cosmic inflation, the rapid expansion that occurred fractions of a second after the Big Bang. Some models suggest that inflation might not have stopped everywhere at once. In some regions, it could still be happening, endlessly creating new pocket universes in a process called eternal inflation. Our universe would just be one of these pockets, drifting in an ever-expanding sea of others. Another version is the many worlds interpretation of quantum mechanics. In this view, Every quantum event with multiple possible outcomes actually happens. All outcomes occur, each in its own branching universe. Every time a particle's position, a photon's path, or even a human choice plays out differently, reality splits. Somewhere out there, another version of you made a different decision this morning, and their life is unfolding along that path. There is also the mathematical multiverse, proposed by cosmologist Max Tegmark. It suggests that all mathematically possible realities exist. Every consistent set of physical laws is realized somewhere. In this grand vision, the distinction between physics and mathematics dissolves, and existence itself becomes the set of all that can be described without contradiction. We have no direct evidence for any of these multiverse ideas. They are, for now, speculative frameworks. And yet, they arise naturally from our best theories, like shadows cast by equations we know to be true. I sometimes think of the multiverse like an endless library, inspired by Jorge Luis Borges' Library of Babel. In this library, every book that can possibly be written exists. Every story, every variation of every story, down to the last letter. Most of the books are nonsense, meaningless strings of words, but somewhere in the shelves is the story of your life, exactly as it happened, and the story of your life with every possible change. If our universe is a single book, the multiverse is the library. In a way, the multiverse replaces the edge of space with a more abstract boundary, the limits of imagination itself. If other universes exist, they are not just beyond our telescopes, they are beyond our physical reach, sealed off by barriers of space-time or laws that prevent crossing between them. For all practical purposes, they might as well be on the far side of infinity. And yet, thinking about them changes how we see our own universe. If we are one among many, then the specific mix of laws and conditions here, the physics that allows galaxies to form, stars to shine, and life to emerge, feels all the more remarkable. It's as if we live in one rare room of the cosmic mansion where the furniture is arranged just right for us to exist. Of course, there's a humbling flip side. In an infinite library, every book exists. If we are in one of many universes, then the fact that we exist might not be special at all. It might be inevitable. Somewhere, by chance, the dice rolled in our favor. Whether the multiverse is real or not, exploring it in thought stretches the boundaries of what we call possible. It invites us to imagine not just a bigger space, but a different kind of space, one where edges aren't physical borders, but the edges of a single story among countless others. And perhaps this is why the multiverse captures our imagination so easily. It gives us a cosmic mirror. Somewhere out there could be another version of us, looking up at their night sky, wondering the same thing. Does space have an edge? We may never meet them. We may never confirm they exist. But by thinking about them, we open doors in our minds that lead to places no telescope can see. And in the end, maybe that's one of the universe's quietest gifts, to make us curious not just about what is, but about what might be. We've spent a long time wandering together through this question. Does space have an end? We've traced the horizons we can see, imagined the ones we can't, followed light across billions of years, and stepped carefully through theories that bend our sense of what's possible. And now, as we reach the final stretch of this slow, star-lit journey, I find myself circling back to something simple. Maybe the most profound edges are the ones we never touch. In science, we like definitions. We like to measure, to mark, to know where one thing stops and another begins. But space does not give us such neat boundaries. The observable universe has a limit, yes, but that limit is not a wall. It's simply the farthest we can see, defined by the age of the cosmos and the speed of light. Beyond it, space continues, or at least, the equations say it should. Whether it curves back, stretches to infinity, or opens into other realms entirely is still unknown. This uncertainty is not a flaw in our knowledge, it's a feature of the universe itself. Some answers may always be out of reach, not because we haven't looked hard enough, but because the rules of reality keep certain doors closed. The event horizon around a black hole hides what's inside, not because we lack imagination, but because the nature of space-time forbids the view. In the same way, the edge of space may forever be hidden behind the curtain of time and expansion. But even if we can't touch the edge, we can still feel its presence, like standing on a foggy shoreline, knowing the ocean stretches beyond sight. The waves still come in, the air still smells of salt. You can't see the far shore, but you can sense the vastness waiting out there. In the same way, every starlit night is a whisper from the unseen. The light that reaches us is proof that something is out there, even if we'll never visit it. And maybe that's enough. Maybe we don't need to cross every border to understand the shape of the land. Cosmology often deals in extremes, infinities, singularities, timeless stretches. But for me, the most moving truth is this: the universe, with or without an edge, has made room for us. For a brief flicker of time, on a small blue world, we get to look up and wonder. We get to ask questions that span from the smallest particle to the largest imaginable space. And that act of wondering connects us to the cosmos as surely as gravity binds stars together. If space is infinite, then our questions are like stones tossed into a bottomless well. The echoes may never return, but the act of throwing them is its own kind of answer. If space is finite and curved, then every journey, of light, of thought, will eventually return to its starting point, carrying with it the quiet satisfaction of completion. Either way, there's a certain peace in knowing that our curiosity is part of a much larger story, one that will continue long after our part is done. I like to think of the universe not as a map with an end-of-page mark in the corner, but as a great piece of music. Some notes we hear now, others will arrive long after we're gone, and some are too far away to ever reach us. But the melody exists, whole and beautiful, even if no one ever hears every note. And so, perhaps the edge of space isn't a line we can cross, but a reminder that there will always be more to learn. That the mystery is not a barrier, but an invitation. That the unknown is not emptiness, but potential. When I began this journey with you, I promised no pop quizzes, no need to remember every detail, just the chance to drift among the stars for a while. We've done that. We've stood at the horizon of the observable universe, floated over the curved skin of a balloon-shaped cosmos, watched galaxies drift beyond our reach, and peeked into the strange rooms of the multiverse. And here we are, still wondering, still moving with the universe as it expands. The truth is, we may never know for certain whether space ends, but in the act of asking, in the long, quiet nights of imagining, we've found something just as valuable: a sense of connection. We are part of this universe, not separate, not outside, but woven into its fabric. Every atom in us has been on a journey billions of years long, born in stars and carried across time to this exact moment. And maybe that's the real edge worth noticing, not the edge of space, but the edge of awareness, the boundary between what we've learned and what lies just beyond. Each time we push against it, it moves, and in doing so, it pulls us forward. So, wherever the universe ends, or doesn't, remember this: the horizon you see tonight is not the end of the story. It's just the next page, waiting for you to turn it.